All right, we're going to continue our discussion on improper integrals 16.4. And so we just kind of discussed and kind of investigated a couple of different problems from indefinite integrals to definite integrals to improper integrals. And so if you look at these three examples, all of these examples are examples of what we call improper integrals, because it looks like we're starting at a value, but we're ending at an infinity, or we're ending at a value but starting from negative infinity, or even starting from negative infinity and ending at negative infinity. What these are called, again, are improper integrals, and they're defined using these rules in this box. And so I can evaluate an indefinite integral if I start at a value and I want to find the area underneath the curve from a value all the way to positive infinity. Well, what I actually need to do is I need to start and end at A and B. But then eventually, if B needs to go to infinity, then I can apply that limit process at the end and make B go to infinity. Similarly, if I'm starting at negative infinity and going to a value, I can actually rewrite it and go from A to B, and then eventually make that A turn into a negative infinity. So we have to rewrite our improper integrals a little bit. We've got to use our fundamental theorem of calculus so that we have an upper limit and a lower limit, always an A and a B. But then eventually, if we need to make that A or B go to positive and negative infinity, we can apply that limit process at the end. Okay? The last one is if we're going from negative infinity to positive infinity. We might actually have to write it out in two different integrals. We can go from negative infinity to a number, and then we can go from that number to positive infinity. And then break up each of these and do our limit process for each of those separate integrals. Okay? We saw in the last video that sometimes when we add up a whole bunch of area and we go all the way to positive infinity, we actually get a number. Remember, we got that area of 2. What that means is that's a convergent integral. Okay? And so we actually get a value for the area going from A to positive infinity. Sometimes, though, when we add up a whole bunch of area, we end up getting that it just keeps adding and adding and adding and adding and adding to itself. We don't actually get an answer because it keeps growing. We call that a divergent integral. And so when we get a real number, we call it convergent. When we don't, and it keeps growing infinitely large, then we call that a divergent integral. So convergent gives you a number, divergent, we just keep growing. Okay? Let's do an example to see what happens on different improper integrals. So in example number 1, we're integrating from 1 to infinity of dx over x. And I don't know about you, but I feel a little bit more comfortable when that dx is brought over to the right a little bit. So I'm going to actually rewrite this problem as 1 over x dx, right? It's the same thing as my original problem. It just looks a little more comfortable to me. So you might want to rewrite it as well. At this point, we can't really go from a number to an infinity. And so we have to rewrite this so that we're going from 1 to b, and then later on, we can apply that limit process in the end. So we need to rewrite this problem so that it is a definite integral from an a to a b, in this case 1 to b, and then eventually we can make that b go to infinity if we need to. Okay, but this is the more proper way of writing these improper integrals so that we can evaluate it. So now we can use our rules for integration, and we can find the antiderivative of 1 over x. Now be careful. If you tried to bring that up and call it x to the negative 1, and you added 1 to the exponent, your new exponent is 0. I hope you didn't divide by 0. So that should have been a red flag for you. Remember that the antiderivative of 1 over x is really the natural log of x. So now I have the natural log of x. We're going to still evaluate it from 1 to b. And then later on, if we need to make that b go really, 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 really big, we can apply our limit process. Let's use our fundamental theorem of calculus to plug in our upper limit. Let's plug in our lower limit. And we end up getting this expression, the natural log of b minus the natural log of 1. And then eventually we want b to get really, 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 really big and approach positive infinity. If you did this in your calculator and you did natural log of 1, the natural log of 1 actually turns out to be 0. So we end up actually just having an expression now that says the limit as b approaches infinity of the natural log of b. And so as b gets really, 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 really big, we end up having a problem that kind of says the natural log of a really big number, natural log of infinity. Well, if you remember the natural log graph, a natural log graph kind of keeps growing and growing and growing and growing and growing. So as x gets really, really big, or in this case b gets really, really big, the natural log of infinity gets big, 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 and it just keeps growing. And so we can say infinity, or it does not exist. There is no definite area. It just keeps growing and growing and growing and growing and growing, and it gets really, 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 really large on this graph. Do you remember what word we used when we don't have an actual real number that represents the area? Yeah, it was divergent. So this is an example of a divergent integral, where the area underneath this graph of my 1 over x from 1 to infinity just gets bigger and bigger and bigger and bigger and bigger and bigger and bigger. We don't actually get a